Hello friends, this is Priyanka. Today we are going to solve a problem on turning moment diagram and flywheel. In this video, we are going to use simple basic formulas instead of using complicated formulas. We are also going to learn how to draw torque crank angle diagram for individual cylinder and resultant torque angle diagram for 3 cylinders by understanding the working of single acting engine. Now first I will read what is the given problem. A 3-cylinder single acting engine has its cranks set equally at 120 degree and it runs at 600 rpm. The torque crank angle diagram for each cycle is a triangle for a power stroke with a maximum torque of 90 Nm at 60 degree from dead center of corresponding crank. The torque on the return stroke is sensibly 0. Determine first power developed, second coefficient of fluctuation of speed if the mass of flywheel is 12 kg and has the radius of gyration of 80 mm. Third, coefficient of fluctuation of energy. Fourth, maximum angular acceleration of the flywheel. So this was the given question. First, we are going to draw the torque crank angle diagram for individual cylinders. Before that, we will understand how this single acting engine works. So here is the piston cylinder arrangement and this piston is connected through this connecting rod to the crank. So as the piston moves from this point A towards point B, there is the forward stroke, and at the same time this crank is rotated from this 0 degree angle towards 180 degree angle. So during the forward stroke, there is the half revolution of the crank is getting completed, and in single acting engine the power is developed only in the forward stroke. There is no any power developed during the return stroke. And when the piston moves from this point B towards point A, then there is the return stroke and the remaining half revolution of the crank is getting completed. Now in this question there are total number of cylinders is 3, that is mentioned, and there is the conditions that is given, that is how they are arranged. So if we observe, the first condition is that for each cylinder crank set at 120 degree apart. So if we observe this diagram for the first cylinder, we will consider the crank is set at 0 degree. So if I take here for the first cylinder the crank is at 0 degree, then for the second cylinder there is the distance that is 120 degree. So I will take here for the second cylinder the crank is set at 120 degree, and for the third cylinder again we have to add 120 degree, that is here 240 degree. So at these 3 angles the crank set for each cylinder is at 120 degree apart. Then maximum torque developed at 60 degree from dead center. So if we observe this diagram, here at this 0 degree we can say inner dead center, and when this half revolution is getting completed at 180 degree there is the outer dead center. So for this first cylinder we can say that inner dead center is at 0 degree and maximum torque developed at 60 degree from dead center, that is 0 plus 60. So here at 60 degree maximum torque developed. Then for second cylinder again we have to add 120 plus 60, that is 180 degree, and for the third cylinder 240 plus 60, that is 300 degree. So at 300 degree the maximum torque is developed. Then torque on return stroke is equal to 0. So that is also mentioned in the question, and therefore forward stroke ends at 180 degree. So power is developed only in the forward stroke, and when return stroke is there then this torque is 0. So we have to show it 0, so there is no any diagram. So we have to show at which angle this forward stroke is getting completed. So for the cylinder first 0 plus 180 degree, because during the rotation of 180 degree, one stroke is getting completed. So I will write here as a 180 degree. Then here 120 plus 180. So here 120 plus 180, that is 300 degree. And 240 plus 180. So if we observe here, there is in one revolution there is 360 degree. Total angle covered is 360 degree. So we can say that here 240 plus 180, that is equal to 420. But for 420 I will write here in this case 360 plus 60. Now we are going to draw torque crank angle diagram for individual cylinder. So if we observe on this vertical line, we have to set the torque in Newton meter and whose maximum value is given, that is 90 Newton meter. So we will take here scale 1 centimeter is equal to 5 Newton meter. And with this scale, this vertical distance, that is at 18 centimeter, we have to take here as a 90 Newton meter torque. Then on the horizontal line, we have to take crank angle and we have to show the total angle in one revolution, that is 360 degree. So we will take here scale 1 centimeter is equal to 10 degree. So according to this scale, we have to take this total horizontal distance, that is equal to 36 centimeter. And we will show some angles at equal interval, that is 60, 120, 180, 240, 300 and 360. Now we will move for the first cylinder. So for first cylinder, inner dead center is at 0 degree, maximum torque is at 60 degree, and this forward stroke is completed at 180 degree. And on return stroke there is no any power developed, and torque on return stroke is mentioned as a 0. So we have to show this. So if we observe at this 60 degree there is the maximum torque. So we will select here one point at 90 Newton meter, and at 180 degree this forward stroke is getting completed. And this turning moment diagram we have to show in the shape of triangle, and that is also mentioned in the question. So I will draw here. So first I will join from this 0 to this point. And then I will join this point to 180 degree. Then we will move for the cylinder second. So I will mention here this is the cylinder 1. Then for the cylinder second, the crank set at 120 degree. So inner dead center is at 180 degree. So we will select this point. Then the maximum torque obtained at 180 degree. So here maximum torque obtained at 180 degree. So maximum torque is 90 Newton meter. So we will select here one point. And this forward stroke is getting completed at 300 degree. So in this way these 3 points are selected. Now we will join these 3 points. Now we will move for the third cylinder. So this is the cylinder second. So for this third cylinder, again the crank angle or crank set at 240 degree. So here I will select point. Then maximum torque is at 300 degree. So for this 300 degree I will select this 90 Newton meter. And then the forward stroke ends 360 plus 60. So this is important point. So at this 360 plus 60, that is total angle is 420. But here in the second revolution of first 60 degree we have to show the here at this point there is the end. So I will show this is the end point of the forward stroke for the third cylinder. So first I will join these 2 points, that is 240 to 300. Then again how to join the next, that is we have to take here next 60 degree. So if I take here with scale next 60 degree, then we have to make here the line parallel to these lines. So these lines are also parallel to each other. So I will take here the line, and here is the point of intersection. Now this point of intersection I will extend here on this vertical line, that is the torque in Newton meter. So I will extend this line. So I will show this the line with the dash. So here is the point. So for remaining we have to join here, because here for 60 degree is the end point. So again I have to take line parallel to this. So this for cylinder 1, 2, for this line I will take the parallel line. So here this is the point. So now we will measure this distance, that is this vertical distance from this 0 to this point. So if I measure this, that is equal to 9 centimeter. So for this 9 centimeter with this scale, what is the value at this point? That is equal to 45 Newton meter. So I will write here, this is the 45 Newton meter. So at this 45 Newton meter, so we have to show this line. So in this way, this torque crank angle diagram for individual cylinder is getting completed. Now we have to draw resultant torque crank angle diagram. So I will show here. So this is the point at 45 Newton meter. So we have to join this point to this point at 90 Newton meter for the cylinder 1. So I will join this with the help of red marker. Then again I have to join this point at 90 Newton meter to the point at intersection of this point, that is the line joining the point 1 to this 180 degree with this intersection of the horizontal line passing from this 45 Newton meter. So here is that point at 120 degree. So I will join this line with the help of red mark. So again I will join this point to this point 2. Again for this point 2 I have to take the point of intersection, that is the line joining this point 2 to 300 degree, and this is the horizontal line passing through this 45 Newton meter. So again I will join this. So here is the point of intersection, that is at 240 degree. So I will join this. Again for this cylinder 3, so this is the maximum torque for cylinder 3. So in the same way I have to join this. So this is the resultant torque crank angle diagram for the 3 cylinders. So we have to repeat this diagram here, because this is the diagram for the resultant torque crank angle diagram. So here we have to again select the same with same scale, that is 1 centimeter is equal to 5 Newton meter and 1 centimeter is equal to 10 degree for this torque and crank angle, and we have to plot here 90 Newton meter and 45 Newton meter, and we have to repeat this diagram that I have shown with the help of the red marker. We will first calculate total torque developed per cycle. It is also called as work done per cycle, and which is equal to area of 3 triangles. Now if we consider for the cylinder 1, that is 1 triangle, then area of 1 triangle is half multiplied by base multiplied by height. So for the height, the maximum torque is 90 Newton meter. So we have to take here as a height 90 Newton meter, and for the base, that is for one cylinder, this cycle is completed during the angle of 180 degree. So we will convert this into radians, that is pi. So we have to take 3 multiplied by half multiplied by pi multiplied by 90, and which is equal to 424 Newton meter. But this total torque developed per cycle, which is equal to mean torque multiplied by crank angle in one cycle. So here mean torque that we have to calculate. So what is the total torque developed? That is 424, which is equal to mean torque multiplied by crank angle in one cycle. So for this one cycle, the total angle which is equal to 360 degree and which is equal to 2 pi. So instead of degrees we have to take in radians, that is equal to 2 pi. So T mean is equal to, that is mean torque is equal to 67.5 Newton meter. So if we observe, according to this scale, we have to plot here 67.5 Newton meter. So if we convert this scale, that is 1 centimeter is equal to 5 Newton meter, then here for 67.5 Newton meter we have to take scale is equal to 13.5 centimeter. So we will mark here one point at a distance of 13.5 centimeter and we will draw one horizontal line which is showing the mean torque. Then again, what is the first question? That is, we have to calculate what is the power developed during the cycle. So for that we will take the basic formula, that is work done is equal to mean torque multiplied by theta. So this is our known formula. So if I divide on both sides by time, then work done divided by time, which is equal to mean torque multiplied by theta divided by time. That is, theta is the angular displacement. So this work done per unit time is nothing but power. So power is equal to mean torque multiplied by displacement divided by time, that is omega. So for this omega, the angular rotational speed n is given. So if we use this n is equal to 600 rpm, then we will get here, that is P is equal to T mean multiplied by omega, that is 67.5 multiplied by 2 pi n by 60. So n is equal to 600. So if we calculate here, 4240 watt, and which is equal to 4.24 kilowatt. So this is the answer of first. Now we will move for the second question, that is coefficient of fluctuation of speed. So its a notation is c to the base s. So for that we will first calculate the maximum fluctuation of energy. So how to calculate the maximum fluctuation of energy? So for that we have to first calculate what is the energy at different points on this mean torque line. So for that we have to first take here the different point. So I will take here the initial point on the mean torque line is the point A. Then here is the second point, that is the point B. Here is the third point, that is point C. Here is point D, E, F, G, and here is the last point, that is the point H. So in this way we have to complete this diagram. When I draw here the one horizontal line, that is the mean torque line, I have to complete this point A and the start point for this cylinder number 1. So this is the triangle shape, that is the resultant torque crank angle diagram for cylinder number 1. This is for cylinder 2 and this is for cylinder 3. So I will join here this A to the bottom point, and in the same way I will join here this line. So in this way this diagram is getting completed. Now from this mean torque line there are different triangles that are getting formed, and now we have to find out areas for that triangle. So here is the first triangle, so I will say this is A1. Here is second triangle, that is A2. Here is A3, A4, A5, A6, and here is A7. Now we have to first find out the areas of these different triangles. So how to calculate the area? So for that I will write here this bottom point, that is this point A, and here this top point I will write here there is a small letter B, and here is small letter A. Now how to calculate the area A1? So for that area A1 I will take here the half multiplied by base multiplied by height. So if I observe for this base I have to measure what is this total length A to B. So for this point B I have to extend this line on this vertically downward direction, and if I measure this length then it is equal to 3 centimeter and it is nothing but 30 degree. So for this 30 degree I have to convert into rad, that is pi by 6. So half multiplied by pi by 6 multiplied by height. So this height is from this capital A to small a distance. So which is equal to 67.5 minus 45. So if I calculate this I will get the area A1 is equal to 5.89 Newton meter. So this area is nothing but the energy that is getting stored. So here this energy is below the mean torque line, and that's why this energy we have to subtract what is the energy at the initial point A, and when we move from this point A to point B, then suppose we will consider at point A there is the total energy E, then when we will move from this point A towards point B, then this energy at that is equal to A1, that is getting subtracted, and at point B suppose here is the area A2 and that is above the mean torque line. So this energy is getting added. So as we move from this point B towards point C, so at this point C, what is the total energy at point B is getting added, the energy which is involved in this area A2, and that is the total energy at point C. So for that, calculation of these areas are important. Now we will move for the calculation of area A2. So again we will take half multiplied by base multiplied by height, because this is area A2 is in the form of triangle. So base we have to measure this total length B to C. So again I will extend this point C in the downward direction. So if I measure what is this distance from this B to C, then that is equal to total 6 centimeter, and which is equal to 60 degree. So for this 60 degree we have to convert into rad, that is pi by 3. And what is height? So height is equal to this distance from B to, I will say this distance on the mean torque line, that is B dash. So this distance B to B dash is 90 minus 67.5. So what is the answer here? That is 11.78 Newton meter. Now if we observe diagram, here is the area A1 which is equal to area A7. So I will say that here this area A1 that is equal to 5.89 Newton meter, which is equal to area A7, and here area A2 which is equal to here A3, A4, A5, A6, A3, A4, A5, A6. Now we have to find out what is the energy at these different points on the mean torque line. So remember, we have to find out the energies on the points at the mean torque line, and then from that we have to find out what is the maximum energy and what is the minimum energy. And if we take the difference in between that maximum energy and minimum energy, then it will give us the maximum fluctuation of energy. So for that we will first consider assume total energy at A which is equal to E. Total energy at point A which is equal to E. Then what is the total energy at point B? So here is area A1 which is below the mean torque line. So A1 is equal to 5.81. So here energy at point B, E minus 5.81. Then energy at C, E minus 5.85 plus A2, that is 11.78. So if we simplify this, we will get E plus 5.89. So energy at D, E plus 5.89 minus 11.78, because here the area is below the mean torque line. So here E minus 5.89. So if we move for that, then energy at E, E plus 5.89, energy at F, E minus 5.89, energy at G, E plus 5.89, and energy at H. So at H again A7 is there, then A7 is equal to 5.89. So E plus 5.89 minus 5.89, which is equal to E. So from this we have to find out where is the maximum energy and minimum energy. So if we observe, for the maximum energy we have to compare here the numbers, but these numbers are same, that is 5.89. So E plus 5.89 we will consider here as a maximum energy, and E minus 5.89 we will consider here as a minimum energy. So if we take the difference in between these two energies, then we will get the maximum fluctuation of energy, and its notation is delta E. So delta E is equal to E plus 5.89. So remember, we have to put the bracket minus in the second bracket E minus 5.89. So if I remove the bracket, here it will become minus E plus 5.89. So this E minus E is getting cancelled. So what is the equation? 5.89 plus 5.89, which is equal to 11.78 Newton meter. Now our main question is that we have to find out the coefficient of fluctuation of speed. But we know that maximum fluctuation of energy, which is equal to 2 multiplied by kinetic energy of flywheel multiplied by the coefficient of fluctuation of speed. So from that formula we can calculate here what is this value of Cs. So what is the kinetic energy of flywheel? So we know that kinetic energy of flywheel is equal to half I omega square. So I is nothing but mass moment of inertia, and omega, that we have calculated, that is 2 pi n by 60. So here this half I omega square, so I is equal to mk square. So here mass is 12, so this 2 and half is getting cancelled. So I is mk square, so 12 multiplied by radius of gyration 0.08 square multiplied by omega square. So omega is 62.84 square multiplied by Cs. So all the values are known. So what is the value of Cs? That is 0.04. So if we multiply here with 100, then we will get the answer in percentage, and that is equal to 4%. Now we will move for the third question, that is coefficient of fluctuation of energy, that is C to the base 2, and which is equal to maximum fluctuation of energy by work done per cycle. So this both we have calculated. So if we put here value, then we will get the answer 0.0278, and which is equal to 2.78%. Then the fourth question is that maximum angular acceleration of flywheel. So angular acceleration is alpha. So here one formula is there, that is maximum torque minus mean torque, which is equal to I alpha. So here torque difference. So what is the maximum torque? So maximum torque is 90 Newton meter, and what is the mean torque? That is 67.5 Newton meter. So we have to take difference, which is equal to I, that is mass moment of inertia, and which is equal to mk square. So m is 12, k is radius of gyration 0.08 square multiplied by alpha. So alpha is 292 radians per second square, and these are the answers.